Today we're going to be talking about the classification of subatomic particles. Classification of subatomic particles. Oops. Okay. Now I'm sure most of you know what an atom is. It consists of a nucleus, and surrounding the nucleus are electrons whizzing around. And that's pretty common knowledge. If you look deep into the nucleus, you'll find that you have different types of particles. You might have perhaps 3 protons and 4 neutrons, let's say. That's a lithium nucleus. And you might think that that's the most fundamental sort of a matter, you might say. Protons and neutrons, in fact, aren't fundamental particles. They are actually made up of fundamental particles. Protons and neutrons are not fundamental. You might have learnt at KS3 or lower years, you might have heard that atoms are the smallest particles, particles that you can't divide. That's in fact not true. You can divide nuclei, you can even divide protons and neutrons into smaller fundamental particles, which I'll now introduce to you. Protons and neutrons actually consist of particles known as quarks. And now let's quickly have a look at the standard model of physics. This is the standard model of physics, okay? Quarks are these particles over here. And you also have things called leptons over here. That include the electron and neutrinos, which we'll come across. And then we have bosons over here. Okay? Now, quarks and leptons are actually part of a classification known as fermions. And fermions, they obey Fermi-Dirac principles, or Fermi-Dirac's physics and statistics, as compared to bosons, which obey Bose-Einstein statistics. But you don't need to know that for now. What we need to have a quick look at are the different types of quarks. We have the up quark, we have the down quark, we have the charm quark, we have the strange quark, we have the top quark, and the bottom quark. This probably won't mean anything to you at this moment in time, and it shouldn't, to be honest. Because the only things you'll need to know about are the up and down quark, which make up protons and neutrons. If you have a quick look at the top at this level, you'll see that the charges are mentioned. These are charges, by the way. And you'll see that the up and down quark have different charges, as do the charm, strange, bottom, and top quarks. And using this information that we have of the up and down quarks, we can then work out what make up protons and neutrons. Okay? So, what we've learned so far is that quarks make up protons and neutrons, right? In fact, there are 3 quarks. 3 quarks make up protons and neutrons. Understanding the fact that the up quark is plus 2/3 and the down quark is minus 1/3, we can then work out that protons consist of 2 up quarks and a down quark, because of the fact that if you have 2 times 2/3 gives you 4/3, minus 1/3 gives you a charge of +1, which we probably have learnt is the charge of a proton, and a neutron will have an up quark and 2 down quarks, because it will be an up quark is 2/3, and 2 times minus 1/3 is 2/3, which gives you a charge of 0, which is correct again. So in essence, that's what protons and neutrons are. If we look slightly deeper, I'm going to quickly erase this off the board. If we look at a slightly bigger picture, let's say, you can have, let's say we have fermions, okay? You can have your leptons over here to the side, leptons, and you'll have your electrons etc. over here. And you also have these things called hadrons, which is a name that we give for particles that consist of quarks. On this section you'll have two things. You'll have baryons and you'll have mesons. Now baryons are the triplet quark particles, and you'll have your protons and your neutrons over here. And the mesons are 2 quark particles. So they're 2 quark particles. This is 3 quark particles. But you don't need to know that for any of your exams, I hope, in the future. But that's just some extra information that you might want to have a look at. Alright. So, now that we've done that, let's see what else we could probably talk about now. If we look at the way we write a chemical equation, or if we represent a nucleus, you can have Z and you can have Y. Okay, so A is the symbol for the element. Z is the nucleon number, and this is the baryon number. What am I talking about? I'm sorry, I'm getting mixed up. This is the proton number. Okay, so this is the number of protons present in a nucleus, which is also subsequently the number of electrons present in a nucleus. The nucleon number is the number of protons plus the number of neutrons, and yeah, based on that you can work out how many how many neutrons there are present in a nucleus by minusing proton number from a nucleon number. What else do we have? Yeah, that's about it. The nucleon number is also known as the baryon number because protons and neutrons are baryons, and baryon number needs to be conserved in a nuclear equation. So, for example, what I'm going to do now is quickly draw a let's see, what sort of decay have you learnt of? You might have learnt of a type of decay called alpha decay, and I'm going to quickly make up something that alpha decays. Let's say we have curium. Okay, curium has an atomic nucleon number of 247, and its proton number is 96. If curium undergoes nucleon decay, you'll lose 2 of your protons, so a curium will become plutonium, which is 94, plutonium, and it will lose 4 neutrons, so that would be 2, 4, 3. Now, what's missing here is, of course, the alpha particle, and we need to balance the baryon number. 247 is not equal to 243. Therefore, the helium nucleus that's emitted will have a nucleon number of 4, or a baryon number of 4, which then balances the baryon numbers, which is important if you are trying to conserve, if you're obeying conservation laws. And of course this will be a 2 because it has 2 protons. So that's something you have to consider, conservation of baryon numbers, and that's very important. And also if we quickly look at some other stuff, let's quickly move on to leptons, which I also want to get in. So lepton, what are leptons? Leptons are these things over here, these things down here. These are leptons. They consist of electrons, muons, and tauons. And each one of them has their own neutrino. You have the electron neutrino, the muon neutrino, and the tau neutrino. Okay? And that's essentially what you need to know. They obey both Fermi direct statistics and you just need to know what they are. Leptons, oh, I forgot to mention, if we compare leptons to hadrons, or baryons, whatever, let's say baryons, okay, because that's all you really need to know. Baryons interact by, so if we have two protons, right, they interact with each other by an interaction known as the strong interaction. Okay? This is a strong nuclear force. The strong nuclear force. And it's carried by a particular particle known as a boson. Now, you might remember bosons from this table down here. These are bosons. And what these bosons are force-carrying particles. They're basically force-carrying particles. Force carriers. Right? The strong interaction. That's why, if you think about it, in a nucleus you have protons really close to each other, and they're not separated. And if you think about it, surely like charges repel, right? But how are they then together in a nucleus? And the explanation for that is the strong interaction. The strong interaction is so powerful that it overcomes the electrostatic repulsion that protons will tend to face. So as a result of the force carriers, the boson in this case, which is known as the gluon, as a result of the gluon's actions, the two protons stay in close contact with each other. Okay? And leptons, on the other hand, they don't feel the strong interactions. So if we have an electron over here, the electron doesn't feel the strong interaction, it actually feels the weak interaction. But you don't need to know much about that at the moment. And if you look down here, you'll see that the weak interaction is carried by this particle, the Z particle, or the W particle, sorry. So that's pretty much what you need to know. The neutrinos that are also leptons, they have zero charge, very similar to a neutron. And of course these electrons, muons, and tauons have -1 charges. An important thing that you might want to notice is this half over here, and this is spin. You'll notice that all the fermions, quarks, and leptons have half spins, so non-integer spins. And if you look at bosons, you'll find that they have integer spins, 1 spins, right? And that's a characteristic that defines protons and leptons. Baryons and leptons, or hadrons and leptons, whatever you wish to call them. Okay, so that's that done. I guess what we could start looking at now is antiparticles, but I'm gonna leave that for the next part of this series. So thank you for now, and I'll see you in a short while.